about job security.
Yeah. Well, I'd like to add a note about Dr. Hartree. When you're at the beginning of an industry like this, people talk about all kinds of things, and one of the things they talked about was what kind of people you needed to run these computers. And because at this time all of these problems were scientific, so people said, well, we need a numerical analyst. So people would say, well, what's a numerical analyst? And they would say, well, we don't know what a numerical analyst is, but Douglas Hartree is one. So, anyway.
Gene, what was the most interesting application you had to work on?
Well, let me go back to say how they ran it at that time. What they did, you would have a scientist who had a problem to do, and then a programmer would be assigned to this scientist to do the problem. Well, to me, Betty Holberton and I programmed the trajectory that was run for the demonstration, and that was by far the most exciting, and I'll tell you why it was exciting. People came, you know, from all over the world and see this, and this program, well, we worked night and day, and I'm sure many of you people here have done the same thing, because they said 2 weeks ahead of time, can you have it ready? And we said, sure. No problem.
Did you have someone named Steve Ballmer working there? This is your interview. I'm sorry. I just couldn't resist.
Well, anyway, so we worked night and day. And right before, it worked fine, except it didn't stop when it hit the ground. It dug a little hole. And I'm sure all of you have had a hard time stopping a do loop at the right time. Anyway, so what we did was to run the trajectory, and we took the punch cards to the tabulator and ran it out and ripped the sheet off and gave it to them as a demonstration. They took it home with them, and then this program actually ran faster than it took the bullet to trace the trajectory. And everybody was, and the other thing was, and you should tell about this because I don't know this story that well, but the Eniac lights flashed up and down because you could see the numbers building up in accumulators and going down. And,
oh, let me tell that story. Well, the Eniac not only did all its calculations behind the scenes because all the vacuum tubes were sticking out the back, but if a tube was activated at all, there was a little neon light in the front of the Eniac, and it showed exactly what position there was what they called what do you call it?
Decade counter.
A decade counter, which meant there were 10 bulbs. 10 vacuum tubes in the back, but every time one of these vacuum tubes lit up, this little neon light in the front did actually light, and that was how we tested it, by seeing when the little neon lights lit up. Well, the photographers came, and this was about 2 weeks before the big display, and they wanted to take a movie of the Eniac working. And when they took this movie, and in those days we only had black and white, and the neon lights just showed up black, so you couldn't see a thing. And we said, how in the world are they ever going to do that? So the story that the newspapers finally picked up was that they went out and they put ping pong balls on there. Because whenever you see a picture of the Eniac, you will see for each number on the decade counter a great big round ball. Well, actually, what actually happened was that John Mockley himself had gone out and bought a case of little white bulbs, and they spent 2 nights, just everybody, all the engineers up, painting 0 up to 9 on 2,000 bulbs. And then they unscrewed the vacuum, the little neons, and screwed in these little real lights. And so, although it was only for that demonstration, but whenever you see a picture of it, you will see, oh, they actually painted the number, 1 to 9 on these little lights. So whenever you see it, you will see this demonstration thing.
And we thought we invented marketing.
Well, wait a minute.
Keep going,
now
please.
back to the problem.
Yeah.
So that was very exciting, and I did work on a problem with Taub. It was called the Taub problem. But really the most exciting program that I worked on was when we turned it into a stored program computer, because very early on it was pretty obvious that I mean, you weren't going to get very many programs run on the Eniac, because not only did you have this problem of programming them, but you had of setting it up and testing them all the time. So early...
I think we have to explain that the Eniac was not a serial machine, it was a parallel machine. And you could have 3 or 4 operations going on at the same time. And different operations took a different length of time. Like an addition, when you added one number to another, just took what they called one add time. A multiplication of a 10-digit number by a second 10-digit number took 14 add times. A division, or a square root, took you couldn't determine how long it was going to take. It depended on the numbers that were involved. So if you were trying to run a parallel operation and you were doing a division here and a couple additions over here and a multiplication over here, you had to make your program so that the thing that was going to take the longest length of time was the one that started up the rest of the program. And you had to be very careful to do this and to balance all your work. So eventually it became ridiculous that you were spending all your time counting pulses when each operation would end, instead of just doing a serial operation. So what Betty is talking about is that eventually, within the year, the Eniac was not redesigned, but extra pieces were put on it so that it was able to operate serially and in what you might call a stored program function.
What happened was a drag function for the shells was put on function tables, and it was built with 3 function tables with 100 entries. And so once we didn't do trajectories, you didn't need these function tables for a drag function. So I think Press and John had thought of this ahead of time,
yes.
But in any case, that you could use this function table to store programs. And what we did was to design an instruction set, and it was designed around a central accumulator. And so the device that they had made was to be able to pull two digits at a time out of the function table, because the function table had 12 digits.
Yeah, 12 digits across, 100
digits across. So anyway, you could pull 2 out at a time, and we had something called a master programmer, which was the control thing of the Eniac, and you fed it into the master programmer, and it decoded it into a program output pulse, which you could use to stimulate an operation, and then you'd go back and get the next one, etc. So then this instruction set looked very much like the instruction set of modern computers. I mean, you had add, subtract, multiply, divide, but it all worked around a central computer, a central accumulator. And this slowed the machine down tremendously. But it was much easier to program, and you didn't have to keep resetting these switches and digit trays, so the probability of errors, went down and everything else. So you could change from one program to another very easily just by changing a bunch of switches on this function table. So we were the only generation that used the Eniac in its original form, because everybody after that, after it was moved to Aberdeen, used it as a stored program computer. And the difficulty with turning it into a stored program computer was to be able to get all the stuff on it, and also to get as minimum an instruction set so we could get it all on, but get enough so we could do all the problems we wanted to do. So that was a lot of fun to do that.
How did your job change and your career evolve with your association with the Eniac?
Well, once the Eniac, they